Hello friends, in this video we will discuss about some properties of the continuous function, So before some examples, let us discuss some theorem about the continuity of a function. So we have a theorem that which tells an necessary and sufficient condition uh, for the continuity of a function by without using an epsilon and delta definition, because in the last lecture we had deal with this definition that for given epsilon greater than 0 there is delta such that f of x minus f of p is less than epsilon for such that okay, or whenever x or mod of x minus p is less than delta. Instead of modulus you can use an a metric d also, because modulus is an particular case of a or particular example of a metric. Okay, so what is the sequential? So what is an sequential criteria for the continuity of a function? Let x d1 and y d2 are any two metric spaces, are any two metric spaces. f from x to y be a function, f from x to y be a function, and p belongs to capital X. This is with us. And f from x to y be a function. Okay, so sequential criteria is that let x d1 and y d2 be two metric spaces, and f from x to y be a function, and p belongs to capital X. then f is continuous at p at phi if and only if and only if for every sequence xn in capital X such that whenever xn converges to p, f of xn converges to f of p, f of xn converges to f of p. This is what about the sequential criteria. And now how we can use this? So it has a proof. In the exam you may ask about prove that this is the sequential criteria for the continuity of a real valued function. Prove that the sequential criteria for the continuity of a real valued function. So proof is very easy. Suppose f is continuous at p belongs to x, and let xn be a sequence in capital X such that xn converges to p, to prove that f of xn converges to f of p, to prove that f of xn converges to f of p. Let epsilon greater than 0 be given be given, and also f is continuous at p belongs to x. Also f is continuous at p belongs to x. This implies that there exists delta greater than 0 such that d1 of x comma p is less than delta, implies that d2 of f of x comma f of p less than epsilon. d1 of x comma p less than delta implies that d2 of f of x comma f of p is less than epsilon. Now for this delta, that is for this delta greater than 0, there exists a not belongs to set of natural number such that d1 of xn comma p is less than delta for all n greater than or equal to n naught by the convergence of sequence, because as xn converges to p, this implies that because f is a continuous function, or this implies that d2 of f of xn comma p comma f of p less than epsilon for all n greater than or equal to n naught. How this comes? This comes from this equation. Suppose this is an equation star, because whenever this happens we have this. So here d1 of x1 comma xn comma p is less than delta implies that d2 of f of xn comma f of p is also less than epsilon. So this comes from this an equation star. So this implies that f of xn converges to f of p as n tends to infinity. So here we had assumed that f is continuous at p belongs to x and xn converges to p, then we had proved that f of xn converges to f of p, and we had proved that f of xn converges to f of p. Now conversely assume that, or suppose, for every sequence xn belongs to capital X with xn converges to p, then f of xn converges to f of p to prove that f is continuous function. We have to prove this, that is f is a continuous function. That is, we had assumed that xn belongs to capital X is a sequence such that xn converges to p, then f of xn converges to f of p, then we have to prove that f is a continuous function. Suppose if possible f is not continuous. Suppose if possible f is not continuous at p, then there exists epsilon greater than 0 such that this is 0, such that if f is not continuous at p, then it should not be follows the definition of continuity. So there exists epsilon greater than 0 such that for all real numbers delta greater than 0, d1 of x comma p is less than delta. But d2 of f of x comma f of p is greater than or equal to epsilon for some x belongs to capital X. For some x belongs to capital X. So what it means? If we take if we take delta is equal to 1 by n, and for each n belongs to capital N, there is xn belongs to capital X such that d1 of xn comma p less than 1 by n, but d2 of f of xn comma f of p is greater than or equal to epsilon, and which is a contradiction because xn converges. What it means? It shows that xn converges to p as n tends to infinity, but f of xn does not converges to f of p as n tends to infinity, which is in contradiction to our assumption. Hence f should be continuous at point p, and hence we get our required result or proof of our theorem. So this is an important characteristic of a continuous function, that whenever f is continuous, what is that characteristic? The characteristic is that whenever f is continuous at p, if and only if for every sequence xn converges to p, f of xn converges to f of p. So this is a very important tool in order to, we can say, disprove that the given function is not continuous at any particular point. In the example, we will see that how this will be used in order to prove or disprove that given function is continuous at particular point or not. Next, algebra of continuous real valued function. Next is what? Algebra of continuous functions. Algebra of continuous functions. What is algebra? If f comma g are continuous functions, c belongs to R, c is a non-zero real number, f and g are continuous, then f plus g is continuous, f minus g is continuous, c into f is continuous, are continuous functions. So this is what an algebra of a continuous function. That is, if f and g are continuous function, then f plus g, f minus g, c into f also, f into g is also continuous function. So it has very simple proof. We can use it generally by using the triangular inequality of a metric, that if f in j are continuous function, then f plus g is f minus g, f into g and c into f are also a continuous functions. So this is what about the algebra of a real valued continuous functions. So in the next video, we will see some examples related to these two properties, that is depending on the algebra of continuous function and this one sequential criteria of a continuous function. So thank you.